This last part of NotesQuest looks at forces. First of all, we're going to define what it is. What is a force? The symbol for force and the units. Then we're going to look at the types of forces. And later on, right at the end, we'll look at mass and weight. Weight being a type of force to do with gravity. And that's a whole other area with an equation. Good news. Then we'll look at what balanced and unbalanced forces means. And then we'll look at Newton's three laws. And from one of those, the second law, we'll get our other equation for this topic, F equals ma. So first of all, what is a force? Well, a force is simply a push or a pull. So if you push or pull something, you are applying a force to it, and that will cause different things to happen to it. So imagine the screen in front of you. If you apply a force to it, two kind of broad things could happen. One, if it was hard enough, could cause it to change its shape. So you could actually break the screen. The other thing it can do is cause it to change its motion. What does that mean? Well, that means it could accelerate, decelerate, or change direction as well. All of those are classified or come under a change in motion. Think about a car. When a force is applied to a car, it accelerates in the direction of that resultant force. Now we need to know the symbol for force. Well, good news. Once again, this is physics. We're sensible. Well, we give it the symbol F for force. Its units, named after Isaac Newton, the scientist who looked at forces quite a lot, is called the Newton and capital N. Maybe you can discover something and get it named after yourself. Newton got there first for this one, unfortunately. Now let's have a look at the types of forces before we look at what we mean by balanced and unbalanced forces. So on here you can see they can broadly be arranged into two categories. Contact forces, and this is when things have to touch for that to occur, and non-contact forces. And these can happen at a distance. You might know magnetism, as we saw in the last topic, can act over a distance. They don't have to be touching those magnets to feel that repulsion. In fact, sometimes you can't even get them to touch. The other one we have in this category is the electrostatic or electric force. And we know that one when we did static electricity. It's all coming together now. Remember, the negative electrons attracted to the positive neutrons. So the opposite charges attract. And that's because of this electrostatic force. We've also got the gravitational force, which has another name, weight, which we'll look at later. And again, that we know that can happen at a distance because the Earth keeps the moon in orbit at a distance. The contact forces, we have, first of all, an applied force. That could just be hitting a ball or you're pushing a laptop. An elastic force, where you can get through there in a spring. As I pull that, it experiences a force in the opposite direction. That's the elastic force. Drag, which we can also call air resistance. So we might see that, and it is basically just a type of friction because you're rubbing against the air, but that always acts in the opposite direction to the motion. So if he's falling this way or she's falling this way, the air resistance will act in the opposite direction. This would be the weight acting down here. The frictional force, well, that's just when two surfaces rub together. A normal force, now that sounds a bit strange, but basically, if you think about it now, your laptop screen or your screen of your computer is resting on a desk at the moment. Well, that desk applies a force upwards, and we just give that the name a normal force. The last one you need to know, which I've added on the bottom here, is the tension force. Imagine a string with a weight on it, as you can see here, and tension would be in that string, holding it up. So let's have a look at some of these forces in action. Now, one way to represent forces is to draw a force diagram. Imagine my table here, and I've got my favourite physics book on here. Now, to show forces, we use arrows to represent them because they have direction and size. The longer the arrow, the more the force. So at the moment, this book obviously has a force downwards, which we're going to call weight, or the gravitational force. You can use either in your exam. Don't just call it gravity, though. It's too vague. Don't call it gravity. You can call it gravitational force or weight. Now, acting upwards, because otherwise this book's now going to go down into the table, is, as we mentioned earlier, that normal reaction force. It's the table pushing back up. And as you can see in this one here, both arrows are equal in size. So we say the force is balanced. That means there's no leftover force. Say the normal force was 10 newtons. We know the weight would be 10 newtons, and therefore the force is balanced. 10 minus 10 gives me 0 newtons, so there is no leftover force. Now this is a bit of a big word here, so it's replaced in physics by the term resultant force. So there is no resultant force when things are balanced. Let's look at another example now, when things are unbalanced. Let's say I take that book up into the air and let go of it. Well, we've got weight still acting down. That hasn't changed because the book still has the same amount of atoms. But we no longer have the upwards force. So now, if weight was 10 newtons, as in earlier, well, 10 minus 0 upwards tells me that we have 10 newtons left over in the downwards direction. So we have a resultant force of 10 newtons. So we say that the forces here are unbalanced. And when forces are unbalanced, we can have an acceleration. Now, it'll accelerate in the direction of that unbalanced force. We know that with this book. It's going to accelerate, which we can represent sometimes with a double-headed arrow, downwards. If we take a car, just as you press the accelerator, we have an unbalanced forward force, applied force we could call it, or yeah, we'll just call it applied force. Backwards we have a bit of friction and air resistance, but we can see that, say the applied force was 100 newtons, and the friction is 10 newtons. The resultant force, 100 minus 10, is 90 newtons, and therefore it's unbalanced, and the car accelerates forwards towards school for your favourite physics lessons. We can also look at the forces acting up and down in this situation, but you always consider them separately from the ones that are acting left and right. That's just a quirk of physics, which is very handy. So the upwards force here would be the normal force from the road, again, and again downwards we would have weight, and these two would be balanced. Otherwise your car's going to take off or sink into the ground, which is going to make getting to school a bit more difficult. So we can have unbalanced forces in the left-right direction, or we call the horizontal direction, but they can be balanced in the vertical or the up-down direction. And we consider them separate because they're 90 degrees to each other. Let's look at Newton's laws now, which are listed here. Number one, law number one, states that all objects stay at rest, that means stay stationary, or continue going at a constant speed, or constant motion, until a resultant force acts on it. What does that mean? That means if the forces are balanced on an object, take the book on the table, the forces are balanced, 10 newtons and 10 newtons, then if this object is at rest, it will stay at rest. If it's already moving, it will just stay moving. Say if it's moving at 10 meters per second, it will keep moving at that. Beautiful example of this would be the Voyager missions, which are shown up here on the left. They've now left our solar system as such. They were launched a long while ago, over 40 years ago. And because the forces are effectively balanced, there's a small gravitational force, but effectively there's no forces acting on this. It just keeps going at a constant speed. I don't know what it is, but it is very fast. It just keeps going at that constant speed until a force acts on it. A resultant force, that is. Not just any force. If the forces were balanced, then it will keep going. Let's look at number two now. This tells us that when a resultant force acts, so this one was all about balanced forces, the first law. When it's balanced forces, the object stays at rest, i.e. stays still, or constant speed if it's already moving at a constant speed. The second one is all about unbalanced forces. What happens here? Well, it tells you that if there's a balanced resultant force, then it's going to be proportional to the mass and the acceleration. It basically tells you the object's going to accelerate. And that means it'll accelerate in the direction that it's moving. If I had to do that as a little diagram, might put Mr. Gardner or someone else running. There's a forward force on me. Let's say it's 20 newtons, and this will cause an acceleration in that direction. That acceleration will be related to the force and the mass, as we'll see later. And let's look at the final law. You might remember this, or might have heard it before, as every action has an opposite and equal reaction. But a better way of wording it is as shown here. For every force on an object, let's take me in this case pushing against a wall, like this. Here's the wall. So for every force on an object, so me pushing on a wall, that way, there's going to be a push in that direction. Tells me that there's going to be an equal and opposite force on another object. So that tells me that if I push on the wall, say with 10 newtons, the wall is going to push back on me with 10 newtons. Now this is quite a complicated one, and we'll look at it in more detail. So for year 9, you just need to memorise that. And the last thing we need to do, if we remember going all the way back to the start, was we had to look at mass and weight. First of all, the difference. So what is mass and what is weight? Now you might think you know, but a lot of people get this wrong. Mass is basically a measure of how much of you there is. So amount of atoms you could think of, or amount of substance there is. its units are the kilogram. Okay, now a lot of times you might say that, oh, I'm going to weigh myself. Well, you're not. You're actually going to mass yourself. Okay, and everyone gets that wrong. So next time, hopefully, you can get that right. Instead of saying, I'm going to go weigh myself on the weighing scales, you're going to go mass yourself on the mass balance. So mass myself is what we mean by weigh yourself. Weight, which is different to mass, is due to the force of gravity. So it's a force. Therefore, given it's a force, its units are newtons. So you can now see that when you say you go to weigh yourself, you're not, because you're not saying, oh, I weigh 80 newtons. It's actually 80 kilograms. So that's the difference there. Now, the important idea with mass is this is the same everywhere. Anywhere in the whole universe, your mass remains the same. Why? Well, because it's a measure of how many atoms you have, and that's not going to change. What does change is weight. And this depends on how strong gravity is, because it's the force of gravity. So if gravity is weaker, or say on the moon, your weight will be less on local gravity. And we represent gravity with the symbol G, as we'll see in a minute. Now you need to know an equation that relates these two. So I'm going to show you that now. And you can see that you have to write about this equation in the formulae section. The equation is weight equals mass times G. What is G? Well, G is the gravitational field strength. Now that sounds big and complicated, but all it is, it tells you how strong gravity is where you are. So e.g. on Earth, gravity has a strength of 10 newtons per kilogram. Whereas on the moon, it's only 1.6 newtons per kilogram. So you can see gravity is weaker. If you want to write this as a symbol, we've got W equals mg. And you need to learn that. To rearrange it, we could work out mass by dividing both sides by g. So mass will be equal to weight divided by g. And if we need to work out g for some reason, then again, divide both sides by mass, we get W over m. This is a very useful equation, and it shows you that when you put your mass in and times it by the strength of gravity, you'll get your weight. And you can see now why your weight differs, because let's do an example here. Mr. Gardner has been bulking up, and let's say my mass is 100 kilograms to make the maths easier. So on Earth, how much does Mr. Gardner weigh? Well, you need to do W equals mg. You need to times Mr. Gardner's mass, remember mass in kilograms, by the strength of gravity, which is 10 on Earth, so we can see down here. That tells me I weigh 1,000 newtons. Let's go to the moon now. Mr. Gardner's just going a little trip to the moon. And you can see that here, if we do weight equals mass times gravity again, the mass is the same, as we say it's the same everywhere. But now we're timing it by a weaker gravity of 1.6. They'll give it to you in the exam. If we do that calculation, we get 160 newtons. And that's why you can jump a lot higher, because my weight is a lot smaller on the moon, so I can overcome it easier and jump higher. In fact, the longest ever golf shot was done on the moon because the weight of the ball is much less. The final thing that you have to do in the formula section is also represent Newton's second law, which was this one, by using an equation, which I'm going to do down here. The equation for this is basically that force is equal to mass. I don't know what I'm saying basically, because it's quite a complicated one. Force equals mass times acceleration. Easy to remember as F equals ma. What does this tell you? Well, if you know the mass of an object and you times it by its acceleration, you can work out what resultant force that object would have. So let's take the example of that book earlier. And it had a resultant force of 100 newtons down. Remember, the resultant is kind of the leftover force. In this case, there's only one force actually on it, so the resultant force F is equal to 100 newtons. Now let's say this book has a mass of 10 kilograms. I've put it on the mass balance and measured that. Now if we put those numbers into our equation, always write the equation out first, F equals ma. We know the force measured in newtons is 100. The mass measured in kilograms is 10. Don't forget mass is in kilograms always, times by A. So that's what, if we want to find out the acceleration of this book, which would be very interesting, well, you can see that we need to get A by itself. So we need to get rid of this 10. Since it's times by 10, we need to divide by 10 on both sides. So 100 divided by 10, remember this line means divided by, is equal to acceleration. So that tells me the acceleration is 10. Hopefully you remember from the last unit, the units of acceleration are meters per second squared. Don't forget the squared up there. So it's a very useful equation. You could also use it in the reverse. You could be given the mass of an object, say the mass of a car is 1,000 kilograms, and its acceleration is 2 meters per second squared. If you want to find the force, the resultant force on that car, well, we just do F equals ma. Numbers go in again, and that tells us that the resultant force on the car is 2,000 newtons. So whatever the leftover force is, it's going to be 2,000 newtons. Remember, this could be because, if we think about it, the forward course force could actually be 3,000 newtons, but because there's 1,000 newtons of friction, that gives us the resultant force that we need of 2,000 newtons. Last thing is just to rearrange this equation, and I want you to think about how you do that, given we've done a very similar equation, W equals mg. In this case, it's just F equals ma. Remember, this means it's F equals m times a. So if we want to get m, we want to work out what m is equal to, and we need to move the a over to the other side. And because it's times, we need to do the opposite, so we need to divide both sides by a. So for m, we'll end up with f over a, or f divided by a. I'm going to leave you to do a and see what that's equal to using the same approach. Thank you for watching.